Heavy hitters. Trends. Google has an interesting webpage called Google Trends, which tracks surging search queries around the world in real time. Right now, there is even a subpage of search trends specifically related to coronavirus. Google tracks the trending search queries not just for the sake of curiosity. Its goal is not only to serve queries, but to serve queries fast. The best way to serve something quickly is to have it ready before it is even asked for. By keeping track of the heavy hitter search terms, a few search terms that make up a disproportionate amount of the search traffic, Google can cache the answers to most search requests before they are even made. Google currently serves billions of queries a day. Given the sheer magnitude of Google's search traffic and the diversity of search queries, it is not obvious how to identify the most popular search queries. Certainly one cannot just make a hash table counting the number of times each search term is queried, since there are too many search terms out there to be stored. More generally, it is prohibitively expensive to maintain any data structure proportional to the input size. Somehow, we need an approach that takes sublinear space. Streaming. We study the heavy hitter problem in the streaming model of computation. In the streaming model, the input is a sequence of items presented to the algorithm one at a time. The algorithm cannot simply write down everything and solve the problem offline because it is restricted to use very little space compared to the input size. For example, if there are n items in a stream, then the algorithm might be restricted to n to the 1/4 space, or even better, big O log n space. Because the space is so much smaller than the input size, each time an item from the stream is given to the algorithm needs to be fairly selective about what parts of the item, if any, it wants to store. We formalize the heavy hitters problem as follows. We have n elements in a stream E1 through En, where each element is from some large universe 1 through m. Elements repeat. The absolute frequency of an element E, denoted f sub E, is the number of times the element appears in the stream. The relative frequency, denoted p sub E, is a fraction of the stream that the element appears in. In a stream of n elements, the relative frequency of an element is the total frequency divided by n. Given epsilon greater than 0, an epsilon heavy hitter is an element with relative frequency greater than or equal to epsilon. The heavy hitters problem is to identify all of the epsilon heavy hitters for an input parameter epsilon greater than 0. Note that there can only be 1 over epsilon many epsilon heavy hitters, which preserves some hope that we can identify all of them with space proportional to 1 over epsilon rather than n. We also consider a closely related problem of frequency estimation. Given a fixed error parameter epsilon greater than 0, the goal is to estimate every element's relative frequency up to an additive error of epsilon. Equivalently, we want to estimate the absolute frequency of each element up to an epsilon n additive factor. At first it might seem impossible to estimate n many counts with sublinear space, except 0 is a satisfactory estimate for all but at most 1 over epsilon elements. If we can estimate the absolute frequency of each element up to additive error epsilon, then one can find all 3 epsilon heavy hitters by considering all of the elements with estimated value at least 2 epsilon. Such a list might also include 1 over epsilon extra elements who have relative frequency less than 3 epsilon but still have frequency greater than 1 over epsilon. Frequency estimation gives more information than just who are the heavy hitters. By knowing their frequency up to some small error, one can also rank them approximately from most to least frequent, such as in Google Trends. Hash frequency counts. We first considered a frequency estimation problem. The goal is to estimate the absolute frequency of each element up to an epsilon n additive factor, where n is the length of the stream. We will solve this problem by employing some of the hashing techniques developed over the last couple of weeks. We create a hash table with W equal to ceiling of 2 over epsilon entries. Note that 2 over epsilon is extremely small compared to the total length of the stream or the distinct number of keys. We also sample universal hash function h from the set 1 to m to the set 1 to w. For each element e presented by the stream, we increase the array cell ah of e by 1. In turn, for each element e, we treat ah of e as an estimate for f sub e. ah of e never underestimates the frequency f sub e, and the hope is that it does not overestimate f sub e by too much. The risk of error comes from other elements' frequencies adding up to more than epsilon n to ah of e. Here the intuition is that the noise coming from other frequencies is spread out by the hash function over epsilon over 2 entries, so we'd only expect epsilon n over 2 error for each element e. To translate expected error to probability of error, we use Markov's inequality as follows. For each element E with probability at least 1/2, we have that the frequency of E is at most AH of E, which is at most a frequency of E plus epsilon n. Proof. We have AH of E is greater than or equal to the frequency of E always because AH of E is a sum of frequencies of elements with hash code H of E, which of course includes E. The expected additive error is bounded above by the expected value of AH of E minus the frequency of E is equal, by linear of expectation, to the sum of all elements D not equal to E, the frequency of D times the probability that D has the same hash code as E. Because H is universal, and the sum of frequencies adds up to n, this is all less than or equal to n over W, and by definition of W, that's less than or equal to epsilon over 2n. Now we have that the probability that AH of E is greater than or equal to the frequency of E plus epsilon n is less than or equal to the probability that AH of E minus F sub E is greater than 2 times the expected value of AH of E minus the frequency of E. And by Markov's inequality, this is less than or equal to 1/2. Amplification. Section 3 shows how to estimate each element with fairly small error with constant probability of error. Our goal now is to reduce the error probability enough to even take the union bound over all of the elements and thus estimate all frequencies up to epsilon n additive error. The idea is to use repetition, and one analogy is coin tossing. The goal is to flip enough coin tosses to get at least one heads with very high probability. With one coin toss, the probability that it is tails is 1/2, which is equal to 0.5. With two coin tosses, the probability that both comes up tails is still 1/4, which is equal to 0.25. But with 100 coin tosses, the probability that all 100 coin tosses come up tails is 1 over 2 to the 100, which is about 0.00000000000000000000007886. The point is that independent trials magnify the probability of at least one success exponentially. For a specified probability of error delta between 0 and 1, the algorithm count mid sketch below makes log 1 over delta independent instances of hash sums with parameter epsilon. For each element E, it uses the minimum estimate over all of the instances of hash sums. The overall data structure fails for an element E only if every instance of hash sums fails, which by the analogy with coins is exceedingly unlikely. Lemma 4.1. For each element E with probability at least 1 minus delta, we have that the minimum over all I from 1 to D of A sub I, Hi of E is less than or equal to the frequency of E plus epsilon n. Proof. We have that the probability that the minimum of I from 1 to D of A sub I, H sub I, E being greater than the frequency of E plus epsilon n is equal, by independence of each of the A sub I, H sub I of E's, to the product from I going from 1 to D, that the probability that A sub I, H sub I of E is greater than F sub E plus epsilon n. Each of these terms is less than or equal to 1 over 2 by lemma 3.1 above, and by choice of D, 1 over 2 to the D is less than or equal to delta. For delta set to a polynomial of 1 over n, the probability of error becomes low enough to take a union bound over all elements as follows. Theorem 4.2. With probability at least 1 minus 1 over n, over a stream of length n, count min sketch with parameters epsilon and 1 over n squared overestimates the total frequency of each element with additive error at most epsilon n. Proof. By lemma 4.1, we have probability of error at most 1 over n squared for each element E. Taking the union bound over all n elements in the stream, we have probability of error less than or equal to 1 over n total. Extensions. One can extend a streaming model to multiple streams in the following distributed model of computation. Here we have several streams simultaneously, each served by an algorithm using sublinear space. The goal is to solve the heavy hitters problem over the combined streams. Count min sketch has a convenient property of being a sketch. To handle multiple streams, we have an instance of count min sketch for each stream arranged so that they all use the same hash functions. To combine the results, we simply sum up the arrays a sub I of hash sums entry-wise. The result is an instance of count-min sketch over the combined streams. Consider the more general model where each item in the stream consists of an element E and a value delta, signifying that we should increase the frequency of count for E, f sub E, by delta. Delta is allowed to be negative with a restriction that the frequency f sub E of each element, which is now the sum of deltas for that element, remains non-negative. This model is sometimes called a turnstile stream, in the sense that a turnstile counting the number of people in an amusement park is always non-negative because each decrease corresponds to a person who entered the park earlier. Count-min sketch adapts immediately to turnstile streams by simply adding delta to a sub I h sub I of E for each instance a sub I h sub I of hash sums. The additive error is now epsilon times the sum of all deltas in the stream.